Starting chapter 4, this is on applications of derivatives. First, we're going to look at 4.1. This is on extreme values of a function on a closed interval. So this is basically what's going to define the extreme value theorem and what happens for a continuous function on a closed interval. So let's sketch a picture. I always hesitate to leave it like I could just copy it over, but I think kind of sketching it out maybe helps a little bit what's going on. So we're going to look at this concept of a function on a closed interval, meaning you actually get to the endpoints. We're going to go from A to B. I'll put those in first, and then you have some sort of function. So our function is going to be, I'm just kind of making this, I have a picture I'm copying, but I'm giving you some examples what it might look like. And it's say, have something like this. Say the function goes up to here. And I'm just looking at how I want to do this. Okay, so suppose the function does something like this, it comes up like this, kind of maxes out like that, comes down, and the function then just does that. And then here the function could maybe, it could go up like this, could stay horizontal or something, or it could go down towards infinity. But that doesn't matter because we're out here past the interval. Okay, but the function does something like that. And here I'm saying the function approaches, oops, I'm going to change that, approaches the x-axis. So this is x. It's kind of funny, I didn't want to draw it anyway. This is x and this is y. So in this picture right here on that interval, this is f of c. F of a would be right about here. So that's my f of a. F of b would be down here. So this is my f of b. So looking at this on that closed interval, what could we say, how could you interpret that thing? So you have your function and it goes here. So this left endpoint, what does f of a tell us? Is that anything special? Is f of a anything special? And no, it's not. Is f of b anything special? Right, in this case, I meant to do it like this. Hold on. I just messed this up last time. Let's do partial eraser here. So I wanted it to looks a certain way and like go down further. So it goes like this. Goes like this, and then maybe it goes like this. So the absolute minimum of the function is actually right here. Well, unless it does this, then there's no minimum. But right there on the interval, so that's the real key here, is on the intervals there's something special about that point. And it turns out, yes, there is. So what we're going to say and label then is on the interval, this is what we call an absolute maximum, abbreviated, of course. And this right here on the interval is an absolute minimum. So basically our theorem says on a closed interval from A to B with a continuous function, right? Can't be any gaps in it. On a continuous function, there exists a maximum and a minimum. And they may occur at the endpoints. That's essentially the punchline of this whole thing. So in this case, this b, f of b, is absolute minimum. It occurred at the endpoint. It's not the minimum of the function. The absolute minimum of the whole function is actually down here, assuming it just kind of goes horizontal, or maybe approaches an asymptote or something, right? And then the absolute maximum of the whole function actually is up here, unless it goes off to infinity or something. So we're really just talking about on a closed interval what's happening. Okay. So here's the definition of absolute minimum, absolute maximum. And then we'll get to the theorem a bit later. So here we go. So here's the definition. So for a function at C on a closed interval I, and we'll just call I, if need be, we'll say it's from A to B like that. The extreme values are defined as this. So extreme values, we have the absolute maximum. So the function has absolute maximum if f of c is greater than or equal to f of x for all x in the closed interval I. And we say it is an absolute minimum if that f of c is less than, of course. So it's absolute minimum if f of c is less than or equal to f of x for all x in the closed interval I. Okay, that makes sense, right? That's the extremum. So that's called extremum as well. So another word, so extremum or extrema of the function. Okay. Now, next definition, this is on an open interval. So let me show you this. So for a function, on, we'd like defined on an open interval from A to B. So you don't include the endpoints. You go all the way up to as close as you ever want to get to A and B, but not including them. So an open interval, we talk about relative or local max and mins. And so this is what the picture would look like. So above I drew a picture of absolute max and mins on a closed interval. Now we want to talk about relative max and mins. So that's when you see all the bumps and dips of the function. So you have some function that, say, looks like this. Let's change colors just because we can. So you have some function that does like this. Just suppose. So on the closed portion, let's say from A to B, let's see where B is going to be. Let's just extend that out farther. Make it easier on me. And then let's say my B is like way out here. So B is out here, and that looks like, on AB, that looks like the maximum value. There's my f of B. My f of A looks like it's right here. Okay, so there's my f of A. But then what about all these little bumps? So basically, what about this and this and this and this and this and this? So those mean something, in other words. So basically the concept here is if you put in a function and you can somewhere put in an open interval around that value. So let's just call that like x naught, and this one x1, and this one x2, and this one x3, x4, x5. You can see that those have what we call, you can put some open interval around those, that they are the max or min value, maximum or minimum value within that open interval. So if you can put in one of those open intervals and that value is a maximum or a minimum, then that's called a local extrema. Because it's localized. It's just localized around that value. I didn't hit that value very well, did I? Okay, but you can see what I mean. So all those are what are called local max or mins. So that's how this is defined. So here's the definition. So for a function f at, and we'll just say c. So those are like all those are my c's. That's like c naught, c1, c2, c3, c4, c5, right? So we'll just call it c. So for a function f at c on an open interval I, and so now I'm saying is from a to b, not including the endpoints. Okay, so for c in I, then f I was actually just defining. So then we have what's called a relative or local max or min. So the relative maximum means basically the same thing, that f of c is greater than or equal to f of x for all x in I. So basically there exists an interval that you can squeeze around it, that it's the maximum or minimum. And that's what we mean by relative. Okay, and then same idea, relative or local minimum is the same idea. Oops, I put an x there. Same idea, f of c is less than or equal to f of x for all x in I. So if you can find I, then, find that open interval, then it's called relative. So there's an existence. So in other words, there exists I that's open such that basically either one of these is true, then f has a local min or max or min. So that's the idea. So if it's just if it's just like this and there's no open interval, then it doesn't actually get to those endpoints. So there's nothing. So if it's just like a line, then there's nothing in that open interval. You can't have an open interval that creates that. Okay, so there's a difference. Now on a closed interval, then it would be the endpoints. All right, so the extreme value theorem basically says there exists a max or min. Okay. So it must be true for a continuous function. So this is called the extreme value theorem. So extreme value theorem says if f is continuous, on D. So it's an interval from, it's just I. It could say I there, it doesn't matter. Whatever book I got this from, they use D. Then there exists a C in the closed interval from A to B such that, remember that backwards thing means such that f of C is greater than or equal to f of x for all x in AB. Okay, so that's absolute maximum. That's what that would mean. This is absolute. There exists an absolute max. The next one will be absolute min. Okay, so and there exists a D, like a different value, in AB such that f of D is less than or equal to f of x for all x in AB. Okay, and that's what we mean by absolute minimum. So the basic idea is, for a continuous function on a closed interval, there exists a max or min. And I like to write that down. All right. So what that's really saying is this. So for a continuous function, it has to be closed on a closed interval. There exists a max and min. It may occur, the disclaimer is, it may occur at the endpoints. It may occur at the endpoints. So you take any function, I mean, it's got to make sense, right? Because it's continuous. Like you have any function, and you do whatever. So you take any function like this, and you throw in some interval. You throw in A, and you go to B. I just put those in there. Then that inside that interval, there must be a maximum or minimum. It may be the endpoint. So the way I drew it, maybe it's this guy here. I don't know. Maybe it's B again. F of B is less than everything else. Let's just pretend that's how I drew it. Put it down here. And then maybe something over here is the maximum. Maybe this goes up like this, and it's the maximum. So it goes, suppose it does this. And then we'll redraw it. It's a nice thing about having this thing. I'll just redraw it again, and it goes down, and that's the minimum, and it goes back up. Then I can go in and I do the same thing really with a pencil. You know, I just go in and erase if I have to. It's a nice thing about this is you can treat it like a pencil and just draw it. I'm gonna have to get a little picky here because I want it to look good. Sometimes just taking your time on this stuff and being really organized is really the key to all this stuff. You just got to be organized about what you're doing, how you're discussing it. I need a bigger eraser now. Okay, so this comes down like that. Okay, so now that's an absolute maximum, or minimum at the endpoint. Pretty much, anyway. Okay, So being careful does make a difference. All right. So here, basically, so this is the absolute maximum. This one does not occur at the endpoint. So there's my C, and then my D equals B is at the endpoint. Okay, so that can happen. Okay, so we better do another video for the rest. Okay, so we'll stop here and do another one for defining critical values and how to find local max and mins, or how to find maximum minimums.